Namaskar. In this sixth talk in my series Fundamentals of Physics and the part fifth of Kinematics in one dimension, we will be defining a set of kinematic quantities which will be helpful in understanding the motion first in one dimensional. Then we will be able to generalize these quantities in later lectures in 2 dimensions and 3 dimensions and understand kinematics in 3 dimensions in terms of these quantities. So far in the previous 4 parts of kinematics in 1 dimension, I have discussed the concept of Newtonian particle and one-dimensional space as a set of points where each point will be assigned a x coordinate and x belongs to the set of real numbers. Position vector of the point of location of the particle at any instant can be described or can be used to specify the state of the particle. At a particular instant, particle is located at a point which has a specific position vector. Time will be taken as a scalar quantity, and again to each instant of time a t coordinate will be assigned where t belongs to the set of real numbers. In the last talk we also defined displacement of the particle in a time interval ti to tf, and the definition was given in terms of the position vector of the particle at instant ti, which is xi, and the position vector of particle at instant tf, which is xf, both being vector quantities. So xf vector minus xi vector was defined as displacement. Now we will move further. We understand that the kinematics of the particle in one dimension can also be described by using this functional approach, that x is a function of time, and therefore at a different instant of the time t, the position of the particle may be at different points in the one-dimensional space. And as described in the last talk, we can use the position time 2-dimensional Cartesian plane to describe the position of the particle at a point p by using x at that particular point. But since x will be changing at different instant of time, we can understand x to be dependent variable and t to be independent variable, and we say that to every member of t or every instant of t we assign a function called x, and that will have a also value which will be a real number but a vector quantity, so there would also be an associated sign. Now for complete understanding of the particle in one dimension motion, what complete understanding would mean? Complete understanding would mean that we know x at every instant of time. So if xt is known for all values of t, we know where the particle will be at a particular instant. So the complete knowledge is contained if we can know x as a function of t for all values of t, right from minus infinity to plus infinity, because in Newtonian physics that is the range, and that is also the range of real numbers. So all values of x and t's are allowed. So at a particular instant ti, let the position vector be given by xi. So xi is the position vector at instant ti and xf is the position vector at instant tf. Then we can define displacement as earlier. Displacement in time interval ti to tf by definition is a vector quantity given by xfi minus xii, which means the final position vector minus the initial position vector, and ti will be referred as initial time and tf as the final time. Once we have defined the quantity displacement vector, we can move further and define more quantities. One has to know in that from mathematical point of view, two quantities can be added only when they have same dimension and same tensorial character. You can't add a scalar to a vector, and similarly a vector which is having dimension of length, and if there is another vector which has dimension something different, then the two cannot be added or subtracted from each other. So by using displacement, however, in defining displacement we have used subtractions, but both are the position vectors and both position vectors have same dimension of length, and so subtraction is allowed. So this mathematical restriction will restrict the range of quantities which I can define. So we define a new quantity for the interval Ti to Tf. By definition, this quantity will be called average velocity, and by definition average velocity for the time interval Ti to Tf, denoted by the symbol delta V Fi vector, will be equal to the displacement delta Xfi vector divided by the time interval Tf minus Ti. So using the displacement vector and multiplying it by the reciprocal of the time interval, and since the scalar multiplication of a vector involves multiplication between a scalar and a vector, so this is permissible operation, and I have defined a quantity called average velocity, which is related to, in definition, to the displacement, and displacement upon time interval is defined as the average velocity. So the definition for average velocity explicitly is final position minus initial position divided by the time interval. But now it is involving two quantities, x which is having dimension of length and time which is having dimension of time. So the dimension of this average velocity will be written as L t minus 1, because t is in denominator, L is in numerator, and power of dimension of length and power of dimension of t is 1. But since t is in denominator, we will say that the average velocity has a dimensions of L t minus 1, and therefore its units will be the unit of meter, unit of time is second, so meter second inverse or meter per second will be the unit of average velocity. This definition we have assumed and we have given in order to build up the theoretical framework. All definitions are given by the proposers of theoretical framework. So average velocity is defined in terms of displacement and time interval, and average velocity makes a sense only for a time interval. Unless you specify the time interval, the phrase average velocity is incomplete. So there is nothing like average velocity of a particle during entire duration of motion. We have to say this is the average velocity for this particular time interval. So that is a very important point. So average velocity in general will be function of time interval, which means that it may have different value for different time interval. So if I increase Tf minus Ti, or if I decrease Tf minus Ti, keeping say Ti same or the otherwise keeping Tf same, then the values will be changing. So this quantity makes sense only in reference to a particularly chosen Ti, the initial time, and a particularly chosen final time. So a particularly chosen Tf minus Ti, the time interval. And with the change in time interval, you can't expect the same value to hold. And that is why we realize that this quantity is not a very useful quantity, because there are infinite such possible time intervals. I can choose Ti from any instant t, and there are infinite values of t possible, and similarly I can choose Tf from any instant of time, and so infinite values possible. So Tf minus Ti, the time interval, so infinite time intervals I can consider, and for each time interval this value will be different maybe, and in that situation this quantity would not be very useful. But there is a special case or type of motion, and which we will now consider, and that is called uniform motion. Uniform motion is a type of motion in which average velocity doesn't depend upon the choice of the interval, and which means it is constant throughout the uniform motion. So whatever Ti I choose, whatever Tf I choose, if I determine it by using any time interval, it would also be applicable for different Ti's and different Tf time intervals. Later, we will establish at the state of uniform motion of a particle in one dimension, or in general in 3 dimensions also. The state of uniform motion can be reduced to the state of rest by choosing a moving frame of reference for describing the physics. And we will take up those concepts. What do we mean by moving frame of reference? But here, just for a hint, that if we choose a frame of reference which in this particular frame of reference is moving with same velocity as that of the particle, then in the chosen frame of reference, new frame of reference, moving frame of reference, the particle would appear to be in a state of rest. And in the last stroke I emphasized that the state of rest, since the position doesn't change with time for all time, so it is not of much interest because change is not involved. So there would be, now in this particular frame of reference, it may have an average velocity which is constant, but you can find a suitably chosen frame of reference in which average velocity will be 0 at all instant of time, and which means the particle will be at rest. Because if particle is at rest, the displacement is 0 for all duration of time. So delta Vfi for uniform motion, which we have defined, will be a constant, and let me label therefore it as a delta V constant and average to remind you that this is an average velocity. So from this relationship, defining relationship, I can write that xfi, the final position, is the average velocity times time interval plus initial position. So the final position can be written in terms of initial position, that it is different than initial position by an amount, vectorial amount definitely, which is equal to the average velocity vector into time interval. In case of uniform motion, I am now restricting myself to uniform motion, which is given here as a title. So remember that uniform motion we are discussing, the relations which I am therefore having on this slide are applicable only for uniform motion. And since this delta V is constant, so okay, I can use this, and suppose I change Ti to t equal to 0. So I assume initial time to be t equal to 0 and write this as an x0 as the initial position, then this can be rewritten in terms of that. So very often we prefer the choice t equal to 0, or initial time is taken at t equal to 0. So what we notice from here, that the curve of xf versus t will be a straight line, because what you are having xf some constant times time plus a constant. x0i is a constant vector, remember. So since x0i is a constant vector, so this is something like that xfi, the final position, is some constant multiplied by t plus another constant. So this will correspond to a straight line in 2-dimensional Cartesian space, which is shown here. That in case of particle uniform motion, if you describe the motion which is described here by this line, then the motion would be along a straight line in 2-dimensional Cartesian space. And you can choose an instant t1, and if at that instant the position is x1, which you can measure from the graph, and at instant t2, so the position is x2, which you can measure from the graph, then you can say that the V average is the displacement x2 minus x1 upon t2 minus t1 equal to tan theta. Here I have not written the, but it's since x1 and x2 both are positive I, and difference would also be in positive I direction, the positive x direction. This is the magnitude of average velocity, and this direction would remain the positive x-axis. And if you learn about lines in 2-dimensional Cartesian space, then you find that the slope of a line is defined, and this would be equal to the slope of the line, and which can also be described in terms of tangent or theta. and theta is this angle which the line makes with the time axis. In general, for an xy line, it is with the x-axis. Here it is with, because on x-axis I have chosen time. So theta is the angle which the line makes with the x-axis, and so this average velocity, if you have this graph, you can determine the average velocity very easily by determining the slope. Slope either you can determine by using this formula or by measuring this angle theta and then getting the value of tangent of theta, which will give you the value of average velocity. Now, equation of straight line, because there are many different types of straight line possible. You would learn in mathematics that the equation of straight line in xy plane is y equal to mx plus c, where m is called slope and c is called intercept. And so y equal to mx plus c is a general equation of a straight line. And so any point on that straight line which will be having specific coordinate x and y would satisfy this equation. Which means every y which is here on the point on the line is given by mx plus c. And here I have shown that there are only 6 different types of lines which are possible. Therefore, in a 6 different, I have shown there can be also lines parallel to x-axis and parallel to y-axis. The lines which are parallel to x-axis will be having y equal to constant, and the lines which are parallel to y-axis will have x equals to constant as the equation. So there will be no dependence on y on x. So y equals to constant means parallel to x-axis, x equals to constant means parallel to y-axis, but other lines which I have drawn are 6 possible types. The line A, B and C, all these lines which you are noticing are making angle less than 90 degree, and all the 3 lines A, B, C are having therefore positive slope, because tangent theta is positive in the first quadrant. But tangent theta is the negative in the second quadrant. In this quadrant, the tangent theta is negative, and since it is theta greater than 90 and less than pi 180 degree, it will be negative. Line D, E and F, which are shown in the green, are making angle more than 90 degree, and therefore the tangent theta would be negative, so slope would be negative. And intercept is shown. Intercept means at where it cuts the, in this case, y-axis. So this is cutting the y-axis below the origin, negative y direction, so I have written intercept negative. B is passing through the origin, so 0 intercept, and C is cutting at this positive y coordinate and therefore positive intercept. So for A, B, C, the slope is same, positive, but they differ by the intercept. For A, the intercept is negative, for B it is 0, for C as shown in the picture it is positive. And similarly I have for D, E and F, I have labeled in the way I have drawn, so I have labeled in clockwise manner A, B, C, D, E, F and not kept any systematics here. But you find that what is D? So D is passing through the origin, so it has intercept 0, whereas E has positive intercept and F has negative intercept. But all these 3 lines are making angle greater than 90 degree, which you can see. And since the angle is greater than 90 degree, so the slope would be negative. So understanding of the straight line would help us in understanding the uniform motion. And in uniform motion, instead of xy axis, as I pointed out earlier, in the Cartesian plane we have time axis and we have the position axis. Time is taken on x-axis, position on y-axis, and I have again shown the same lines A, B, C, D, E, F, and now the average velocity, because is equal to the slope of the line, and therefore average velocity will be positively oriented, which means towards plus x-axis in case of the line A, B and C, and it is negatively oriented in case of D, E and F. So it will be a negative number tan theta, and here tan theta which we have obtained will be a positive, and the same thing is the intercept, that at initial time whether it was having a negative x coordinate or 0 x coordinate, means at origin, or positive x coordinate, that can be determined. So you can read certain information from the curves of straight line if you know that the particle is performing uniform motion, and if the line is given to you, then you can make out whether the average velocity is positive or negative. You can make out whether the intercept is negative 0 or positive, Also, if you can measure the angle theta, then you can also determine the average velocity, or by drawing two perpendiculars, choosing 2 points on the line and drawing perpendiculars on x and y axis, which here means time and position axis, you can find by using that definition which I have given earlier, the displacement and the time interval, and therefore you can find the average velocity. So this two-dimensional Cartesian space approach helps us in understanding the mathematics which is associated with the definition of average velocity. So with this concept of average velocity, again summing to that, if you can measure at two instants t1 and t2, the positions are x1 and x2, the average velocity will be given by this, and it is always equal to tangent of theta, where theta is the angle which it makes with x time axis. For uniform motion, since the average velocity is constant throughout the duration, it can be considered as a good quantity to measure the change in the state of the particle, and position of the particle at any later instant can be determined by using average velocity, and if you already know the position at one instant. So for solving a problem of uniform motion in one dimension, what I need? I must know position at one instant, at least any instant, t1, t2, 0, whatever, and the average velocity. And since average velocity is constant, if I know position at one instant and average velocity, I know position at all other instants also. So this is sufficient information. So if you have to solve a problem of uniform motion in one dimension, you need to know only the average velocity and non-position at one instant. Thus, in case of uniform motion, we need not define anything more, and that looks like very good thing, because the ultimate objective is to know the position at all different instants of time. I have already said that if you know x at all instant of time, you know where the particle will be at all instant of time, and you have complete knowledge of the particle or the motion of the particle. So position vector at any instant can be obtained by using the information of average velocity and the knowledge of the position at one time in case of uniform motion. But all motions are not uniform motions, and there will be very few examples. In fact, in day-to-day life where you will find uniform motion, you find examples of non-uniform motion. So as I have said, that uniform motion in Cartesian space look like a straight line. The non-uniform motion would be any other curve which you can draw smoothly. Draw any smooth curve on this two-dimensional plane that would represent a non-uniform motion case other than a straight line. So this is the curve sample shown here, and here at time t1 the position is x1, time t2 position is x2. So you can determine that what we have done in case of uniform motion, that would work. But the curve is not a straight line, and since curve is not a straight line, when you define average velocity, which you will define by the same definition, the definition is not dependent upon the nature of curve. So average velocity in the interval t2 minus t1 will be different if different t1 and t2 are chosen, which you can see from this graph. That if you change the t1 place here, it will be a different value. If you place t1 here, keeping t2 same, it will have a different value. If you place t1 here at t2 same or any different point, it will have a different value. So this is very important, that average velocity change, even if I keep one of the quantity t1 fixed and change t2, or t2 fixed and change t1. So what t2 we should minus t1 we should use, because if we are changing t2 minus t1, then the value is changing, and since I have already pointed out there are infinite choices of t2 minus t1 available, and since a description of particles motion in one dimension, it requires specification of infinite quantities, it would not be making a good sense or meaningful. So we realize that the limitation of our definition of average velocity in describing the non-uniform motion. Though average velocity was a good quantity for describing the uniform motion, it is not useful. And so Newton also realized this problem, and what he could notice, that the kind of mathematical knowledge which was available at that particular period of time was not suitable for describing the motion in one dimension, you can say, or in three dimensions. So Newton had to invent a new mathematics, and the similar mathematics or same mathematics was independently invented by Lambage. Newton called the new mathematics functional calculus, and the Lambage called infinitesimal calculus. And the two are same, and now we understand in a better language and better terms called differential calculus. So what we realize that we have just moved in the course of theoretical development of physics, and we find that we need a new mathematics to understand. And Newton could invent it at proper time, so he could develop the ideas which are very helpful in development of Newtonian mechanics and Newtonian theories. Credit who has invented it first, it's a debatable question. There is no uniform acceptance, and so credit should be given, in my opinion, to both Lambage and Newton for inventing this interesting branch of differential calculus. And at the same time, therefore, it means that you will have to learn differential calculus, and which I will not discuss in detail, but you will have to learn differential calculus to learn theories in physics or fundamentals of physics. No one can understand fundamentals of physics without understanding differential calculus. The word calculus was in a sense communicating that a new way of calculation, the calculations which were earlier done and now done using calculus are different. So you can take it like a new way of calculation was invented by Newton and Lambage, and which is helpful in our understanding of motion of particle. So differential calculus and its inverse operational integral calculus we will have to learn to understand the theories of physics. But before we move further, I can now explain you how we arrive at the differential calculus, the concepts in differential calculus or the notions of differential calculus. This physics example would also help us the understanding the mathematics of differential calculus in a better manner. So since average velocity is dependent on time interval, which you can vary, which you can decrease, which you can increase. So what we can do, we can decrease it, keep on decreasing and making it smaller and smaller. But you can't decrease it to 0, because you know that division by 0 is not allowed in mathematics. And since 0 you can't choose, so still it will be a non-zero. Whatever small value of time interval you take, it will be a non-zero. But now an important philosophical as well as mathematical question arises: how small I can decrease to the time interval other than 0? And so a new concept was introduced in the mathematics, and that is called the concept of infinitesimal. It is for sure that infinitesimal is not equal to 0. It's not 0, because division by 0 is not allowed, but division by infinitesimal is allowed. But it is smaller in magnitude than every possible real number which is not 0. So for all non-zero numbers comes to your mind, it would be a smaller number than that. It's a very interesting topic, and maybe I would have another lecture, full lecture on the concept of infinitesimal as well as the concept of infinity, and those lectures can be understood only when we understand Zeno's paradoxes. But a separate series of talk would be given on that. So keep watching my YouTube channel for that. To understand infinitesimal, we have to introduce a new kind of mathematical things and operations like limits, and whereby taking a limiting value such as tending to 0. When we say taking a limit tending to 0 of a particular variable tending to 0, what it means, it is not equal to 0. It will never be 0, but the difference between it and the particular value will decrease and become infinitesimally small. And there are therefore techniques of obtaining limits of functions by imposing these conditions, and those techniques you have to learn if you have to master this mathematics. However, in our course, if we know certain laws of differential calculus and some formula, we would be able to work out and solve problems. But any initial understanding of differential calculus would require the learning of the methods of mathematical methods which are used for determining limits, and for that you must consult a book. So in mathematics, a limit is the value that a function or sequence approaches. There is a typos as the input or index approaches some value. So the concept of limit is important. Thus with limits we have a tool to consider the value of average velocity when the time interval is becoming smaller, infinite small, which means tending to 0 but not equal to 0. So we define a new quantity based on it, because we can now have a mathematical method, and what we need in fact in all cases, and which can be later understood in proper terms, that the curves which you can observe in xt space must be smooth, and there are other notions of differential calculus which one should understand to understand this. But what we find that when we decrease t1 minus t2, if I have moved t1 towards t2 and as small as I make, I find that the change t1 minus t2 is on the basis of decreasing. When t1 minus t2 becomes extremely small, the average velocity is approaching a particular value, and that particular value is a limiting value or is a value which I can be interested in, because that limiting value when t1 minus t2 is tending to 0, I can attribute to, so t2 minus t1, since my t2 I am considering, so t2 minus t1 tending to 0, that value I can consider to be specifically assigned to this instant t2, and therefore this makes us a basis for defining a new physical quantity which we call instantaneous value or of velocity, or instantaneous velocity at instant t2 or at any instant t. And how it is defined? It is defined by using the calculus, and as I have already pointed out, that calculus was invented by Newton and Lambert, and you have to learn calculus, and there are techniques in calculus and there are concepts in calculus which one should master if one wants to understand the physics. And I hope that you will make an independent exercise over it. There are many kinds of calculus, and where here I say calculus, I means calculus of real numbers. So differential real calculus, real differential calculus, and later real integral calculus will be important for us in coming lectures. But in much advanced lectures towards the end of the series, we would also be needing to learn different kinds of calculus in between also, and towards the end maybe a calculus which would be much different than what we need to know now. The position function we consider as a continuous function of time, and continuity is defined in calculus. Derivatives are defined in calculus. Limits we know how to calculate, and that all knowledge once you acquire, then you can define the velocity of at a particular instant or instantaneous velocity. Instantaneous velocity by definition is this: the limiting average velocity when t2 minus t1 tends to 0. So t2 minus t1 tends to 0, either you can say it is the limiting velocity at t1 or limiting velocity of t2, doesn't matter, because the 2 points have become 1 point. So you can write it t2 also, you can write it t1 also. So here I have said that if t2, the final position, I bring closer and closer to this, then I can know the instantaneous velocity at t1. So t2 I am bringing closer and closer, and to know the instantaneous velocity at t1, what I need to know, I need to calculate the limiting value when I am decreasing t2 towards t1, and then what will be this limiting value. Already pointed out, differential calculus has all these notions of limit, infinitesimal, continuity, derivatives and derivative of derivatives, differentiability and analytic function. And there is an associated integral calculus based on the inverse operation of differentiation called integration. And remember that in physics later we will find that the curve of x and t must be an analytic function. I have said x is the function of t, but x must be an analytic function of time, and that allows you that x is differentiable, and differentiability is involved in the definition of analytic function. Wherever it would be explicitly become important, we will take note of it and I will say something more. But right now I assume that you know the differential calculus, and if you have not learned the differential calculus, first learn the differential calculus. And once you know the differential calculus, you know that this thing would be written as dx by dt t equals to t1 on. This is not a ratio, this is single symbol. It would be called differentiation of x with respect to time, or to more accurate, this is the first derivative of position with respect to time, or first differential coefficient of position with respect to time. But this is one symbol. You can't consider it as a ratio or something like that. We have chosen that we would be writing this symbol in this particular manner, and it helps us in understanding. But don't think that the d and x and d and t are separable here, or even dx or dt are separable here. It is a single symbol which is indivisible in that sense. You can't resolve it further. And the definition, this is by definition, that's why I use triple equal sign. So equivalent sign. So this is an equivalent to this. By definition, this would be called the derivative of position with respect to time. So instantaneous velocity is defined as the first derivative of position vector with respect to time. And since average velocity is constant, and so even if you change the time interval, it remains same. So what you will find that the instantaneous velocity at all instants in uniform motion will also be constant. So when average velocity is constant, instantaneous velocity is also constant in case of uniform motion. So we can also define uniform motion as a case that instantaneous velocity is constant. And later we will find that the average velocity I have used here as a concept, and it's good physical quantity for uniform motion, but I am using it only as a concept here, and in our later discussions we will, whenever I will say velocity, I will mean instantaneous velocity. So the default meaning of velocity will be instantaneous velocity, because this adjective instantaneous is a very big and it takes space in writing, so we would omit in speaking as well as in writing instantaneous. But velocity vector or velocity will mean instantaneous velocity. In literature also, sometimes some books use velocity vector and some books use velocity. And so we would be, even if we don't mention vector, we know that velocity, instantaneous velocity, average velocities are vector quantities, and they have the dimensions of meter and L and T minus 1. Both have same dimension, because only limiting operation will not change the dimension. So dimensions of the average velocity and instantaneous velocity is same, unit remains same, meter per second. So for any example of motion, since position will be considered as a function of time, and in mathematics the differential calculus is applicable whenever x is a function of time or whenever a variable is function of another variable, and we can define the derivatives. Like here we have said that x, which is a dependent variable, t, which is an independent variable, so chosen here, and we say that dx by dt is the first differential coefficient of x with respect to time, and by definition it will be written as v at t. And similarly you can do, if you know the xt as a mathematical expression, then you can obtain the vt as a mathematical expression by using this definition. And then for obtaining the value at a particular instant, you will have to replace t by t1. So t symbol can be used in two different manners. Here when I am using t, t is a variable, so it can have any value of t, and t1 when I am using at least a specific instance of t or a specific value of t, the instant. Okay. So t equals to t1 is the instantaneous value at a particular point or at a particular instant, and vt is generally an expression which can be obtained from xt. If you know, then you can obtain the vt. So if you know the position as a function of time, you can obtain mathematically the velocity as a function of time. So that is the summary so far. A particle in one dimension, we would use position vector, and the derivatives of position, we have defined the first derivative as velocity, and we have also defined the average velocity and displacement vector earlier. The both position vector and velocity vectors depend upon time, which means are function of time, whereas the displacement vector and average velocities are defined for a chosen interval. So these are quantities which would not be very much useful later on. Displacement thou would be useful, but not the average velocity, but position and velocity vector we will continue. Once we have defined a quantity like this, we can go ahead and define more quantities. So once you learn a technique in mathematics, generally people improve upon that and introduce more quantities. So if x is function of time, so is the v also function of time. So in the manner in which I have defined dx by dt as v, I can take the derivative of v also with respect to t. And if I take derivative of v with respect to t, I come to a new quantity which I name, and names are given by us acceleration. So similarly, I can say that if at instant t equals to ti, the particle will have some velocity vi, and if at instant t equal to tf, it has velocity vf, then I can define first an average acceleration. An average acceleration will be equal to the final velocity minus initial velocity vectors divided by the time interval. And in the same manner as I have defined from average velocity to the instantaneous velocity, I can move from average acceleration to the instantaneous acceleration. And as said earlier, whenever I will use word acceleration later in the talks, it would refer to instantaneous acceleration. Average acceleration is a quantity which, if asked in a particular question, you have to answer in that manner, and it is for a specific time interval. But just like that average acceleration, if you measure, then you find that the different values you are getting for different time intervals. So it is better to define a derivative and a new quantity in terms of derivative, and that is what we have done, acceleration here. So now you know that after introducing instantaneous velocity, I have introduced two more quantities, average acceleration and acceleration or instantaneous acceleration. The acceleration will have different dimensions because it is rate of derivative of time with respect to it is the derivative of velocity with respect to time. It can also be written as, because velocity itself is the first derivative of position with respect to time, so you can call it the second derivative of position with respect to time. So an alternative way of understanding acceleration is, it is the second derivative. If you take derivative of derivative, that is a business in differential calculus, that after making one differentiation, if you differentiate again with respect to time, you get the second derivative, and you can repeat also on third derivative, fourth derivative, and so on. So what I find that I can say acceleration is the first rate of change or first derivative of velocity with respect to time, or it is the second rate of change or second derivative of position with respect to time. But it will have a dimension because there are the two times I have taken the derivative, so the time dimension is -2 and the length dimension remains +1. So it is LT -2, and unit therefore will be meter second -2, which means the power raised to -2, or meter per second square, or meter per second, whatever you wish to say. So acceleration will be non-zero in non-uniform motion. In uniform motion, since you know the velocity is constant, so wherever you will determine average acceleration, it would always be 0. So uniform motion, I can say that average velocity is constant, instantaneous velocity is constant, but average acceleration is 0, and acceleration is also 0 in uniform motion. But in other motions which are not uniform, I call non-uniform motion. In non-uniform motion, acceleration would be of our interest because it is not 0. Then once you learn this, and since you know in physics, and a physicist or a mathematician have tendency to keep using the knowledge which they have acquired and improving the scenario. So once I have defined the second derivative of position as acceleration, I can define the third derivative of position, which will be the second derivative of velocity, which will be the first derivative of acceleration, as jerk or jolt. Jerk or jolt will be having the dimension of L t raised to power -3, but it can be defined by this mathematical relationship. So if in a question jerk is asked, you can obtain the jerk by 3 times differentiating the position with respect to time, or twice differentiating the position velocity with respect to time, or differentiating acceleration with respect to time. And by differential calculus, if you know xt, you can know vt, and you can know at, and then you can know jt based on the differentiation. So to obtain the jerk as a function of time from the position as a function of time, 3 differentiation operation would be required. But I can continue, there is no limit to it. So the term is also named for the fourth derivative of position, and that is called snap or jounce. Snap or jounce you can use for fourth derivative of the position, or it is the rate of change of jerk, as jerk is rate of change of acceleration with respect to time, or first derivative of acceleration with respect to time. Similarly, the snap is the first derivative of jerk with respect to time, or you can say the fourth derivative of position with respect to time. Fifth derivative in literature is known as Crackle or Flounce. So you can use the word Crackle or Flounce, whichever you like, and if you find a question where Crackle or Flounce is asked, what you have to do? You have to determine the first derivative of snap, which is second derivative of jerk, which is third derivative of acceleration, which is fourth derivative of velocity, and fifth derivative of position with respect to time. All derivatives here defined with respect to time. And similarly, the sixth derivative is called Pop or Founce. And these are definitions we have introduced, and the names have been selected by us. So don't question why we have made a particular use. It is always depend upon something which you observe in our life, and the names of the quantities are derived from our personal experiences and our vocabulary already existing. So these names have been chosen. Jerk, and you understand that sometimes we say that the motion is jerky, a car ride is jerky, and nobody likes a jerky car ride. People do like a ride in which the jerk is zero, and therefore acceleration, if occurring, is occurring in constant manner only, but not in jerky manner. If acceleration is changing with time, then it means there is a non-zero jerk, because the derivative measures how it's changing with respect to time. So jerk, snap and higher derivatives are also important, and are more important. Later in our theoretical analysis we may not be using it much, because we will restrict to very simple cases. But on real applications of physics, in engineering application, in engineering design, in designing a road, in designing a railway track, in designing the engineering gadgets and appliances sometimes, or even say for launching a rocket, or a Hubble telescope, or anything in space, we need to consider the higher derivatives also. And whenever the necessity would arise, I would always point it out. But in most of the later discussions, you will find that we may limit, and there is a reason because of we may limit, and it's a common practice in teaching physics that we limit ourselves to acceleration and don't consider the cases where jerk is non-zero, where snap is non-zero, or higher derivatives are non-zero. Why these quantities are important? That's very simple. That if position is changing from one to another, so there is a velocity. But if velocity initially is zero and then you make a certain velocity, as you know that if a car is in a state of rest, you want to attain a certain velocity. So if you want to attain a certain velocity from zero, you will have to build it up, and so there will be acceleration. But acceleration is also initially zero. Suppose it was in a state of rest, so acceleration is also zero. In state of rest, all these quantities are zero. So to make the velocity from zero to non-zero, you need acceleration. But to have that acceleration, because earlier the acceleration was zero, you need jerk. And since jerk was also earlier zero, so to have that particular jerk, you need a snap. And because again, with the same logic, you can move ahead and you can say that Crackle just is required to have snap, and if you have snap, only then you can build up a jerk, and if you have jerk, then only you can build up acceleration, and if you have an acceleration, then only you can build up velocity. So in the real cases, the higher derivatives are significant and sometimes are manifested. But later, when applied examples of what kind we will consider, definitely I would explain these things in detail. But there is no limit and you can continue to define the derivatives in this manner. And that is the beauty we have from mathematics that allows us to define a set of physical quantities. All these physical quantities, velocity, acceleration, jerk, snap, are having different dimensions and different units. They cannot be added to each other because they have different dimensions. And so one has to be very cautious when dealing with them. They have different dimensions, maybe have same dimensions of length, but different dimensions in comparison to time. And so a jerk can be subtracted from a jerk, but a jerk cannot be added to acceleration. Now in literary saying, sometimes you may misuse such a word in a language in describing a phenomenon. But a jerk is something different which cannot be added to acceleration. And similarly, an acceleration cannot be added to the velocity. Now to conclude today's talk, I wish to include in my slides the rules which you must learn. Differentiation rules. How differentiation of sum, what is the differentiation of a constant is 0. How sum rule can be applied. How product rule, differentiation of product of two functions. How division rule is applied. And the beauty in the differentiation is that we have a chain rule. And if you have to differentiate something x in terms of say t, and then if there is an intermediate variable, then you can differentiate x first with respect to that intermediate variable and then intermediate variable with respect to t, and can obtain from those two derivatives the derivative which is mentioned here in the chain rule, which is interesting, that if a function of x, so f is a function of g of x, where g is a function of x. So what we can do, we can derive or differentiate this function f with respect to function g, and then we can differentiate function g with respect to this function x. This chain rule makes differentiation very easy in many cases. But division rule is there, which you must know the formula, and product rule, you must memorize the formula before my next talk. And the differentiation formula, what is the differentiation of x raised to power n with respect to x? It is n x raised to power n minus 1. What is the differentiation of an exponential, differentiation of a log, differentiation of sine, cosine, tangent, cotangent, sec, cosec? All these formula are given here. I will not waste time in my video lecture to speak out each formula, but all these formulae you must remember and would be very useful in solving numerical problems as well as theoretical problems. So we assume, or I assume, that meanwhile before the next talk you will learn all these formulas, and more formulas are available in the books of table of integrals and differentiation formulas. So you can consult the book also. As far as my physics discourse is concerned, I can rely upon the books and table of formula and get a formula from there as and when appropriately required. But when you do such problems infrequently, then you would come to know that after a few applications you get habitual to it, or it fits into your memory and you can very easily recollect a formula whenever required. So if I ask what is the differentiation of sine of ax plus b with respect to x, you would be very easily able to reflect it and recollect it and give it. But doing the physics also required doing differential calculus. If you can't do differential calculus, if you can't do differentiation, you can't move ahead in what I would be discussing. So this is the prerequisite, and therefore certain exercises at least you should do from any source or from any book of differential calculus. And these abstract problems which we solve in differential calculus mathematics course are also help us in building our understanding of differential calculus. And the formula for hyperbolic inverse, these are also required in physics. So I have mentioned all the formula. And I leave you with one problem, and this problem we will discuss, and more problems we will discuss and try to make out from our understanding of kinematic quantities, set of kinematic quantities which we have so far defined for describing one-dimensional motion of a particle in one dimension. So consider a particle whose position at any instant is given by this function of time. X is a function of time is given to you, a plus bt plus ct square plus dt2. dt cube. So it's a polynomial and the highest degree is 3. So it's a degree 3 polynomial. So you have where A is given to you, B is given to you, C is given to you, and D was also given to you. And I have assigned here values of A, B, C and D, keeping in mind a topic which we will later discuss, significant figures. So A is known, B is known, C is known and D is known, but remember A, B, C and D each have different dimensions and units, and appropriately every term, because if X is having dimension of length, every term appearing in addition should have a dimension of length. So A should have a dimension of length, BT should have dimension of length, so B should have a dimension of length upon time. CT square should have dimension of length, which means C must have a unit of length and time inverse square, so meter per second square, and you realize that D should have meter per second cube. So it is clear to you why D should have meter per second, so that BT has meter and CT square is also in meter, DT cube is also in meter, because X is in meter. Any such a linear expression, all terms appearing must have same dimension and should be expressible in same units. You can't add meter and inches and things like that, okay, without converting. So given this example, which the information, necessary information is given here, you can do this exercise to find average velocity and average acceleration, and average is defined for a time interval. So I have given the time interval also from 1 second to 3 seconds. And also determine the instantaneous velocity and instantaneous acceleration at time t equal to 2 seconds. And also try to plot the curve from the range t equal to 0 to t equal to 4 and how it looks like. And also obtain the expression, because you have expression of x with respect to t. By differentiating with, you can find velocity. By differentiating velocity, you can find acceleration. By differentiating acceleration, you can find jerk, and so on. So also obtain expression for the higher derivatives too. In the next talk, we will first take up a few numerical problems, so you have a better understanding of the things which I have discussed so far, and then we will also consider the special case of what is called uniform acceleration. Again, a special case, uniform motion we have already discussed, and uniform acceleration, and in relation to that, we will come to discuss Newton's equations of motion, which would be helpful in solving more problems in very easy manner. With this, I conclude my today's talk, and I hope that you are liking my lectures. Please click the like if you like the lectures, subscribe to my YouTube channel, and click bell icon for getting the notification. And thank you very much for being with me in this series of video talks. I hope you are enjoying it.